All right. So, welcome to the first lecture on optical properties of materials. This kicks off our class on engineering optics. And the reason I want to talk about the optical properties of materials is because we'll learn about how light behaves in materials, and then we'll start scaffolding that out into how light behaves in lenses and then other objects, right? But first thing you have to understand is how light behaves in a material. And the hard thing about optics, really, in the end, besides how complex it can get, is the fact that the behavior of light is explained through electromagnetic waves and also through quantum mechanics. It's also a discrete object, right? It's a wave-particle duality. For the start of this, though, optical properties of materials, we can normally just talk about the electromagnetic wave part of it. And so we know that electromagnetic waves can exist along a literally a spectrum, right? Of different wavelengths. We got very large wavelengths, which are radio waves on the order of kilometers, to microwaves, which exist in your microwave, quite literally, which are on the order of millimeters, to infrared and invisible light, which is what we're going to be talking about in this class, which is on the order of hundreds of nanometers in microns, roughly. And so higher energy wavelengths, which are shorter, right? Because as we move in this direction on this plot, we increase in energy for our photons that carry this energy. Ultraviolet light is on the order of about 10 to 100 nanometers. X-rays are less than a nanometer, and gamma rays are even on the order of picometers, so on the order of the size of a nucleus. And like I said, we're going to be focusing in on this range right here, which is the optical range. And the optical range is interesting because it interacts strongly with matter, right? Radio waves tend to pass through matter. Radio waves, infrared and microwaves their wavelength, their size of their wavelength tends to be on the order of the amount that a molecule moves in terms of thermal motion. It excites thermal motion. So we get a lot of thermal interactions with microwaves and infrared. And ultraviolet, X-ray, and gamma rays are energetic enough that they actually blow up and destroy atoms or molecules, right? So if an ultraviolet ray is high enough energy, so like ultraviolet C, you probably heard about ultraviolet C with a lot of disinfectants for COVID-19. Trying to really push that now. Really, it disinfects everything because ultraviolet C, photons are energetic enough that if an atom absorbs it, it actually excites electrons to high enough energy states that they either leave the atom or the molecule or create new molecules, because these excited molecules then latch on another one and eat each other or form new combinations. That's a bad thing when that happens to your DNA, which is why if you have a lot of ultraviolet light, you can get skin cancer and things like that. All right, so let's talk. We're going to ignore the temperature part of this for now. We'll talk more about that when we talk about ways of generating light much later in the semester. But the important part is that when an electromagnetic wave comes in contact with a material, it interacts with it with the charges in it. So when an electromagnetic wave interacts with material, what it interacts with is the charges. So let's look at a model atom here on the bottom, right? And we have a nucleus here. We have, let's call this an electron cloud, like this. cloud. When the electromagnetic wave comes through, right, there's an electric component and a magnetic component. The electric component pushes and pulls on these electrons, and so it'll actually move this electron cloud over. Not much, actually. It's a very small amount. But it actually moves this electron cloud over, and then the electric force. Let's put that in this box over here. Electric force restores the position, because we have all these positive charges in the nucleus, right? And our net charge for our electron cloud is now somewhere over here. And so we have a net force trying to restore this electron cloud back to being centered over the nucleus. And this briefly creates, this distance between these two here, this d, briefly creates a dipole. Which, as you know from your Physics 2 class, and possibly a circuits class. I don't know if they talk about that much in circuits, but dipoles, right, also radiate an electric field that dies off fairly quickly. It dies off with, I think, the third or the fourth power of the distance away. But these dipoles then can interact with other induced dipoles to absorb energy. And it's actually quite a bit like the damped oscillators you learn or see in your controls class. But imagine a whole just a stupid number of them, right? These are atoms or molecules that we're talking about here, interacting. And remember, with damped oscillators, the amount of energy they absorb or pass through is very dependent upon the frequency of the forcing that you're doing. And it's the same with materials. So the amount that they absorb is dependent on the frequency, which is why some materials will absorb strongly in a color or multiple colors, and others will pass light through them without interacting. So light waves come through, they move these electric clouds. This is true up until the energy of the photons becomes high enough to start exciting electrons. Then the same effects occur, but energy absorption only occurs if the electron can reach a stable energy state. Okay. So what does it take then for a material to be transparent? What does it take for us to have glass that allows light to pass through it apparently unimpeded? Well, that's not true, right? There's some absorption, a small amount of absorption, but there's some absorption. And what it requires is that when the wave comes through and interacts with our damped oscillator atoms and molecules, that the resonant frequency is different than the photon frequency, and really it's quantum effects prevent that absorption. Frequency not equal frequency of the photon. Photon is not equal to the frequency of the resonant frequency of the material of the atoms, right? Not equal to resonant frequency. And quantum effects have to prevent absorption. So, whoops. This is why this resonant frequency here is one of the reasons why crystalline materials usually actually scattering light's a little bit different thing. So what happens when light interacts very strongly with the material but is not absorbed? Well, what ends up happening is if it interacts very strongly with the material, let's go back to our little atom model here. This electron cloud moves over and then comes back, right? But this cloud has inertia. And even if an electron is excited to a higher energy state, but then comes right back down, that takes time. It takes time for an electron to get excited and then relax and come back down to its previous energy state. So all of this takes time, and that time causes the electromagnetic wave to slow down. The degree to which it slows down is called the index of refraction. Okay, so n is equal to c, the speed of light in a vacuum, divided by v, speed of light in a material. And this is actually a complex number. In glasses, we don't really use the complex part because it's an absorption, right? So this is equal to n of refractance plus I times n imaginary, so real and imaginary components. And this deals with absorption. Absorption of the energy of the photon. And this deals with transmission. Right? So n itself can be quite high. So yeah, we're only, like I said, we're only going to talk about the real component for the first third of the course, and then we'll start talking about the imaginary component. When we start talking about like reflectance off of metals, absorption, and things like that. It can be quite high. For example, moissanite has an index of refraction of 2.645. Diamonds are 2.415. These are materials in which the light is very slow, so the wave, right, is interacting very strongly with the electrons in the material, but it's not being absorbed by the electrons. It's being either re-radiated or passed right through. Water is 1.33. Cooking oil is about 1.45. Air is slightly more than 1, not much. Not enough more than 1 to really care about unless you're doing really very sensitive measurements. And vacuum is 1.0 because obviously that's the speed of light in a vacuum divided by the speed of light back is 1. Incidentally, right? The reason why diamonds sparkle is I'm sure you saw in one of your classes. Let's see if we can. If you take a rope, right, with a thick part and then a thin part attached to it like this, and you send a wave down it, part of that wave is going to get reflected back, and part of it will be transmitted by the difference in the weight per unit length of the rope. That reflectance at an interface happens with light too. It's a little bit different because we can get total internal reflection, which we'll talk about. But that's what causes diamonds to sparkle, because there's such a huge change in the ability of light to pass, or the speed of light when passing through it. It's just like having a very thick rope and then a very thin rope. You'll get a lot of reflected light coming back. So when you shine a light into a diamond, it bounces around on all those faces and comes back out and makes it sparkle. Incidentally, moissanite sparkles more. So there's an argument to be made that that makes a better sparkly ring. I don't know what that means, but cool. So from what we set up here, the degree to which a material interacts with a photon or a electromagnetic wave is dependent upon its frequency, right? The properties of this electron field, especially with molecules where it gets very complex because the electron electron clouds are overlapping for the different atoms and interacting with each other can be quite complicated. So the index of refraction obviously is a function of wavelength or frequency, however you want to talk about it. Frequency. So if you look on the internet, you can very easily find descriptions of the index of refractions of materials as a function of wavelength. So here we have wavelength in microns, and this is just a screen capture of a website. Do I give you guys the website? I don't. Oh, refractiveindex.info here. Here we're looking at a material called BK7. It's a type of glass, a formulation for glass, which is very popular for making lenses out of. Right? Not cheap lenses, but certainly not expensive lenses. It's just a really kind of standard lens material. And what we can see is that over the optical wavelengths, which are from about 400 microns here to about 600 or 700 microns. That's about as far as you can see with your eye. You can barely see a little bit longer than that. Depends on the quality of your cones, right? The color sensing parts of your eye. And here we can actually see something interesting. The wavelength, the index of refraction of our material over this range of wavelength actually varies a decent amount, right? It starts off at 1.514 and ends up at 1.554 or something like that. So this actually causes a problem, right? Because when we end up designing optical systems, we will design them for a certain wavelength, about 0.5. You'll notice that the index of refraction given for this material is a single number, 1.5266. And that design wavelength is actually here, 437 nanometers about. But that's clearly not the actual wavelength, right? As the wavelength changes, as the color of the light changes, the index of refraction changes. This is going to cause problems, particularly with imaging systems that we call chromatic aberration. We'll get into aberrations later, but you can imagine if you're trying to design an optical system with a certain behavior, if you change the wavelength, the behavior of the whole system is going to change, and that's going to cause problems for your design. This dispersion, there's different ways of describing the amount of dispersion. And the dispersion is the name for this variation in index refraction as a function of wavelength. There's the Ab number, there's chromatic dispersion, there's group velocity dispersion, and they all have different uses, and we'll talk about them later. But the really cool part is that they give you formulas for the index of refraction as a function of wavelength. And the ray tracing tools that I've given you actually have this formula built into it for a lot of different materials. So if you ever see when the lens definitions, you see PS, ends, and then BK7. What this is doing is this is actually calling or referencing this formula, which I typed out in a different part of the program. So let's talk about the dispersion just a little bit. The Ab number, or Abe numbers, it's the Ab number. V is equal to V is equal to the index of refraction at what's called the D line minus 1 divided by the index of refraction at the F line minus the index of refraction at the C line. So the A, B, C, D, blah, 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 F lines are specific wavelengths. Oops. Related to spectral lines of specific materials. So if you excite, for example, let's say mercury, you pass a current through a mercury vapor, the atoms will be excited. You know, you have a little atom, and then around it you have electrons zipping around like this. Those electrons will jump up to a higher orbital, higher energy level, and then they'll come back down. And they can come down to different amounts, and each one of those amounts corresponds to a different wavelength. And so certain materials will give off very, very specific wavelengths of light. And this used to be how they produced what I would call very clean light, right? Light that has just a single wavelength. The light that's illuminating your room right now is very broad, right? It's producing a relatively broad range of wavelengths. But when you're trying to do research, like discover the index of refraction as a function of wavelength, you want to make sure that you know the wavelength very specifically. So what they used to do is do things like make these mercury arc lamps and then select just one of those wavelengths using a prism or something like that. We can talk about that later. Now we have lasers that are very narrow, but they didn't have those until about the 70s, I think. Is when 60s and 70s is when lasers started being invented and widely used. So cool. So just a quick review. The index of refraction is a measure of how strongly light interacts with the material without being how strongly light interacts with the material. The absorptivity, which is the imaginary part, it's not actually, it's related to the absorption, describes the absorption. We're going to mostly deal with very low absorptive materials, so glasses, things like that, in the first third of the half the course. So we're not going to deal with this at all right now. We're only going to deal with these indexes of refraction. And the index of refraction tells us how slow the material goes, how slow light goes through the material. So an index of refraction of 2 means that the speed of the light in the material is half that of the speed of light in a vacuum. So higher index of refraction materials have light going slower. This is useful, and we'll talk about it in the next lecture, why that's useful. All right. Let's call that a day.